Hello everybody, my name is Fatma Kılınç-Karzan, and today I will talk about my research on characterizations and applications of rank 1 generated cons. This is joint work with Alex Wang, my PhD student from CMU CS, and CJ Argue from CMU Med. In this presentation, I will first introduce the concept of rank 1 generatedness and our main question. Then I will provide the motivation for studying this property. I'll continue with some properties of rank 1 generated sets and discuss a number of sufficient conditions guaranteeing this rank 1 generated property, as well as the necessity of these conditions in a particular case of interest. I'll close with some takeaway messages. Many of you may not have heard the terminology of rank 1 generated before, so let's formally define it. In this presentation, we will be interested in sets of the form S defined by the intersection of the positive semi-definite cone with a possibly infinite system of linear matrix inequalities. A closed convex cone S that's of this form is called rank 1 generated if all of its extreme rays are generated by rank 1 matrices. As an immediate example, the positive semi-definite cone is rank 1 generated. In this research, we are interested in when a given set S that's defined by a number of homogeneous linear matrix inequalities is rank 1 generated. Rank 1 generated property is important in studying the semi-definite programming relaxations of quadratically constrained quadratic programs. General quadratically constrained quadratic programs take the form of minimizing a quadratic function subject to a number of quadratic constraints, and any one of these quadratics can be non-convex. Here's a typical example. QCQPs are used in various problems in optimization, statistics, and machine learning. Classical examples include max-cut, max-click, or clustering sparse regression. More generally, any polynomial optimization problem or any mixed binary programming problem can be written as a QCQP. So QCQPs are highly expressive, but they are NP-hard in general. Therefore, STP relaxations are often used as an approximation for QCQP. There is vast literature on approximation guarantees provided by STP relaxations. The classical examples are developed in the context of max-cut, famous Commons-Williamson result, or Nash-Ross pi/2 theorem, or matrix cube results, and so forth. In general, the optimum objective value of the QCQP and the optimum objective value of the STP match when a sequence of feasible rank 1 STP solutions converge to the optimum. However, it's NP-hard to check whether we have this objective value exactness of the STP. Nevertheless, sufficient conditions that ensure tightness are of great interest. And recent work has focused on sufficient conditions guaranteeing STP objective value exactness or STP convexal exactness. These results naturally exploit the given objective function of the QCQP. In this talk, we are interested in STP exactness conditions that are oblivious to the choice of the objective function. Let us take a look at the QCQP and its standard STP relaxation. Any general QCQP can be transformed into a form where the objective and all of the constraints except one are homogeneous. Also, it can be reformulated in a lifted space by introducing a matrix variable X and an additional non-convex constraint, ensuring that the rank of this matrix is equal to 1. Then dropping the rank 1 constraint leads to the standard STP relaxation. Note that the feasible region of the STP relaxation is nothing but the intersection of a set of form S script M with a single affine equation. The rank 1 generated property has a number of important implications for STP exactness. Let us first see the implications for STP objective value exactness. When our domain is defined in particular by a cone of the form script S script M, then whenever this set is rank 1 generated, for every possible objective function, we have this equality saying that the SDP relaxation is exact. In addition, when our domain of the QCQP is such that we have an affine constraint, then intersected with a set of script S script M, then again, under a minor technical condition, which is satisfied, for example, when the SDP region is bounded, we can show that the rank 1 generated property of script S script M set ensures that for every choice of the objective function, the SDP relaxation is tight. In addition, under strict feasibility assumptions, strict dual feasibility, or this particular assumption here, the rank 1 generated results can be translated into exact convexal descriptions via projected SDP domain, particularly this set, or via projected associated SDP epigraphical set. So to summarize, we observed that rank 1 generated property under minor additional conditions provide SDP objective value tightness and convexal characterizations. The rank 1 generated property is also relevant in the context of sum of squares hierarchy. In particular, it characterizes when this hierarchy converges in exactly one step. From a different perspective, the rank 1 generated property of spectaedra can be thought of as an analog to the integrality property of the linear program relaxations of integer linear programs. In particular, the rank 1 generated property plays an analogous role to the integral polyhedra, that is, the exactness results that are oblivious to the objective function. These are conditions that are well known as total unimodular matrices or total dual integrality in the case of integral polyhedra. The literature on rank 1 generated sets dates back to S lemma. And thus far, this literature has focused on either specific problem instances such as S lemma or positive semi-definite matrix completion or truss region subproblem and its variants, or the cones obtained by adding finitely many homogeneous linear matrix equations and the resulting algebraic geometry-based connections. In contrast, in our study, we examine rank 1 generated property for general cones with possibly infinitely many linear matrix inequalities, and this generality allows us to handle sets defined by conic constraints as well. To recap, given M and the associated SM, we are interested in identifying sufficient or necessary conditions on M that guarantee that SM is rank 1 generated. Given a set M, we will quickly switch from studying SM to sets defined by linear matrix equations of the form Tm. Indeed, we will see that Tm is simpler to analyze than Sm. When M is finite, lifting Sm into Tm prime is possible, but this lifting does not preserve the rank 1 generated property. We next examine rank 1 generated property of Sm and Tm through their facial structures. These results are particularly instrumental when we analyze the spectral sets defined by finitely many linear matrix inequalities or equations. First, note that Sm is rank 1 generated if and only if every face of Sm is rank 1 generated. This result is analogous to the statement that a polyhedron is integral if and only if each of its faces is integral. As a corollary, we deduce that Sm is rank 1 generated implies Tm is also rank 1 generated. Note that the reverse implication does not hold in general. When M is compact, Sm is rank 1 generated if and only if every one of its proper faces obtained by setting a number of linear matrix inequalities into equation is rank 1 generated. And when M is finite, we can establish that Sm is rank 1 generated by showing that the set Tm prime is rank 1 generated for every subset M prime of the set M. Our results on the facial structure of rank 1 generated sets have immediate implications. In the case of a single linear matrix inequality, S is rank 1 generated if and only if T is rank 1 generated. Moreover, in this case, a well-known consequence of S lemma is that Sm is always rank 1 generated. This also inspires for an immediate sufficient condition for rank 1 generatedness. When multiple linear matrix inequalities defining script S, script M are non-interacting pairwise, that is, every extreme ray of the set script S, script M is an extreme ray of the sets script S individual MIs for some I, the resulting set is rank 1 generated. S lemma gives an immediate characterization for a pair of linear matrix inequalities to be non-interacting as the condition that there is a non-trivial combination of the underlying matrices that is positive semi-definite. Thus, we arrive at our first explicit characterization of a sufficient condition for rank 1 generated property, as stated here. Another conclusion of our facial characterizations is that in the case of two linear matrix inequalities, even if they may possibly be interacting with each other, S is rank 1 generated if and only if T is rank 1 generated. In terms of developing a toolset for rank 1 generatedness, the following operations are useful in reasoning about the extreme rays of the set script S, script M. They are in particular characterizing a few operations that preserve rank 1 generated property. The first one states that a new set obtained by intersecting a number of rank 1 generated sets is rank 1 generated if and only if the intersection operation does not create new extreme rays. The next result refines this further when script M can be partitioned into non-interacting set of constraints. And here's our characterization of the non-interacting assumption, which states that if a group of constraints are tight at a given matrix, then the remaining group of constraints are strictly satisfied. The rank 1 generated property of a set is intimately connected to the existence of non-zero solutions of underlying quadratic systems of inequalities or equations. In particular, S is rank 1 generated if and only for every non-zero vector in the set script S, we have that the range of X intersected with a particular set, the script E, is non-trivial. Note that the characterization of the script E not only depends on the set of matrices defining LMIS, script M, but also the particular matrix X that we are examining. By definition, the script set E contains a simpler set corresponding to the solutions to a homogeneous system of linear matrix equations. Here, the N set is composed of simply the vectors small x defining rank 1 matrices that belong to the set script T. In fact, T is rank 1 generated if and only if for every matrix X from the script T set, the range of X intersected script N is non-trivial. In fact, it suffices to check this condition for only matrices X of rank at least 2. And when N contains a homogeneous hyperplane, then we will immediately observe that the range of X of a rank 2 matrix intersected with N is always non-trivial, and therefore the necessary and sufficient characterizations of rank 1 generated property for both the set T and the set S are automatically satisfied. Therefore, these sets are rank 1 generated. Hence, given script M, we would like to know when N contains a homogeneous hyperplane. Note that N script M is obtained as the intersection of N sets of the individual matrices M in script M. Thus, we can seek out a characterization in the simplest case of when script M is just a single matrix M. In such a case, we have a simple characterization. N set associated with a single matrix M contains a homogeneous hyperplane, such as X such that A transpose X equals 0, if and only if there exists a vector B such that M can be written as a specific indefinite rank 2 matrix of the form AB transpose plus BA transpose. This result then implies that for any set of vectors from script B, both of the sets S and T defined by the particular set of rank 2 matrices parameterized through B are rank 1 generated. Note that by interpreting the vectors in B as generators of a dual cone, we observe that the constraints in S can be written as a single conic constraint of the form XA in K. Hence, we deduce that adding the conic constraint XA in K, where K is any closed convex cone, results in a rank 1 generated set. Using our tool set, we can further show that the cone defined by the constraint XA in the second order cone and a particular linear matrix inequality defined by the matrix modeling the second order cone is rank 1 generated. Thus, we recovered the well-known result that the STP relaxation strengthened with a second order cone RLT constraint is exact for the variant of the Terrace region subproblem with a single linear inequality constraint. Let me close by summarizing the case of two linear matrix inequalities. We have identified the following two conditions as sufficient conditions for rank 1 generated property. Condition I covers the simple case where the two linear matrix inequalities do not interact with each other in a non-trivial way inside the positive semi-definite cone. In fact, in this case, the two linear matrix equations corresponding to these matrices only interact with each other on a single possibly empty face of the positive semi-definite cone. And furthermore, on this face, the two linear matrix equations impose the same possibly trivial constraint. Condition II covers the important case when the two linear matrix equations interact in a non-trivial manner inside the positive semi-definite cone. Indeed, this is the case where the associated T set is the convex hollow union of two faces of the positive semi-definite cone with a very particular intersection structure. Now, these are, we have seen that these are sufficient conditions. Furthermore, through a non-trivial analysis that crucially relies on Dean's theorem and the consequence of Bezout's theorem from algebraic geometry, we can show that in the case of two linear matrix inequalities, these conditions are not only sufficient, but also necessary. This then gives a complete characterization of the rank 1 generated property in the case of two linear matrix inequalities. Note that this is a generalization of the well-known well-known characterization given by S lemma in the case of a single linear matrix inequality. Furthermore, both directions of this theorem admit small certificates. When SM is rank 1 generated, we can certify this by either providing a non-trivial aggregation weights resulting in a positive semi-definite matrix, or doing spectral decomposition of the matrices M1 and M2, and exposing their specific rank 2 structure, sharing a particular vector A. When SM is not rank 1 generated, presenting a post-definite matrix in the set T of script M will certify that condition I fails. This is through Gordon-Stampkir theorem. Also, if either rank of M1 or rank of M2 is greater than or equal to 3, then the spectral decomposition of the corresponding M matrix, MI matrix, certifies that condition II does not hold. If their ranks are less than or equal to, if their ranks are less than or equal to 2, then M1 and M2 are both indefinite rank 2 matrices, and writing the specific indefinite characterization of these matrices and identifying that the 4 vectors involved in their characterization are indeed distinct will give the desired certificate that shows that this condition II fails. Let me close with some takeaway messages. Rank 1 generated property presents a beautiful geometric view on subsets S of the positive semi-definite cone. Also, under minor assumptions, rank 1 generated property provides SDP objective value tightness and convex exactness results. We discussed a toolset for rank 1 generated property. In particular, we have introduced a number of sufficient conditions for rank 1 generated property. And we have shown that these 2 sufficient conditions are not only sufficient, but also necessary in the case of 2 sets defined by 2 linear matrix inequalities. As future work, we are interested in identifying other rank 1 generated sets or operations preserving rank 1 generated property and sufficient conditions, or possibly establishing the necessary of those conditions. Thank you for listening to my talk. I hope my talk has gotten you interested in rank 1 generated property. Our paper has other tools and sufficient conditions for rank 1 generated property, but there are still many more open questions. If you are interested in further details, I strongly encourage you to look at our paper, and please do not hesitate to reach out to me as well. Here is a list of references mentioned during my talk. Let me close by thanking the organizers for putting together a wonderful event despite the pandemic circumstances and inviting me to give a talk.